Okay, so here we're gonna build off what we talked about last time. We're looking at maps, right? And we're wondering, well, how many colors does it take to color a map? Right now, the one thing about maps, right, is that they are always planar. Borders don't cross the plane. Okay, so the map question about colors always we can relate that to just kind of generalize it in a more abstract notion. We can ask ourselves what is the maximum chromatic number of any planar graph. All right, so it solves a much bigger set of problems, right? So as it turns out here that uh, so this question was posed in 1852. I guess initially, right, what people started to notice, well, one particular mathematician, I believe in England, started to notice he was coloring the counties and noticed that it could be done in 4 colors, right? And then a larger question arises, well, can I do this? What's the minimum number of colors needed, right, to draw a map so that any counties or countries, whatever it may be, if the shared borders have to be different colors, right? So it was posed then, and then in 1976, these two people, Appel and Haken, actually solved this problem. Right now, this was the first major theorem that was proved with the assistance of a computer. Right, so it was actually done through essentially running through different configurations. Right, and as it turns out here that everyone's right intuition or just the application of it was always that it seemed to be it could be done with at most 4. Right, and that is turned out to be true. Right, and that introduced us to our theorem, the 4-color theorem, which again won't go through the proof, right? Seeing as a very computational based proof. The 4-color theorem, right? So this stated that every planar graph has chromatic number less than or equal to 4. So we have a upper bound, right, for any, and again, right, it's important to realize that this is just for planar graphs. Okay. Excuse me. Okay. So every planar graph has chromatic number of less than or equal to 4. Again, depending on what the planar graph looks like, maybe it takes 2 colors, right? Maybe it takes 3 colors, right? But 4 would be the absolute max here. Right, now, for something that is not planar, right, we have what is called Brooks's theorem. Right, so now what this theorem says that for any graph G, chi G, right, the chromatic number is less than or equal to delta G. Now here, delta G, what that refers to is the maximum degree, right? Degree of the vertex, right? So we look for through all the vertex, the vertices, and whatever the maximum degree is for all of the vertices, that would be our upper bound. Okay. Now this is going to work when in every case, right, unless G is a complete graph or an odd cycle, right, in which case the chromatic number of G is equal to max degree of G plus 1. Okay. Now in terms of this, the complete graph, or we could see complete K3 here. And so we could see it looks like this. And we could see, well, each vertex has a degree of 2, right? The chromatic number here would be 3, right? And it's just the nature, since for complete, right, all of these, each vertex has an edge going to every other vertex. So we have to account for all the edges going to those vertices, right? And also the vertex that it's emanating from, hence the plus 1. Now this odd cycle one, right? So we're we're bounded there if we have, again, for the same reason here, right? So let's say if we had a different type of graph here. Excuse me. Right, so in this case here, the chromatic number here is the degree plus 1. All right. And then here, in this case, if it weren't not necessarily complete, but just had an even cycle here. Okay, so here when we see here the max degree here is 2, and we can color it with 2 colors, right? If we think of this would be the first color, this will be the second color, this will be, again, back to the first color because it's not shared with the other one. Second color, first color, second color, right? So we could see those edges are not touching any vertices with the same color. Right, and again, we could see that that becomes impossible, not only if it's complete, but even if I just had an odd cycle here. So if I were to take away one of those vertices and have a similar type formulation where we just have a cycle here. All right, and notice if I try to do the same thing, we have one second color. I can go back to the first color, second color, but now I can't go back to 1 here because I'll be sharing an edge with 1 here, right? So here we have an odd cycle going through these 5 vertices, so I would need another color. Hence the max degree. Each of these has a max degree of 2. But the nature of that odd cycle means I'm going to need that plus 1 color here to have a proper coloring. Okay. Now, an example that we can use this for, like a type of coloring graph, is let's say that we had so for this example, let's say we suppose 5 students are enrolled in the following courses. All right, so Here's the student. And then the courses. All right. And so we'll have 1, 2, 3, 4, 5. And student 1 is enrolled in math, CS, and history. Student 2 is enrolled in math and bio. Okay, and then student 3 is enrolled in CS, art, and then student 4 is enrolled in history, bio, and art, and student 5 is enrolled in CS and bio. All right, and let's say that we're trying to figure out how many time slots are needed so that students don't have an exam at the same time, right? So they don't overlap here, right? So one way we can transform this into a graph here is we can have the vertices be the subjects here. So let's say M for math, H for history, and then CS for computer science, A for art, and then B for biology, right? And we can have an edge if a student is taking those classes, right? There's a student that is in both of those, right? So for instance, student 1, right, we should have one between math, CS, math and history, and also between history and CS. Okay, because they share a student. And then for the second student, math and bio, so we have here, okay. And then CS and art share a student. And then student 4, we have history, bio, and then bio and art, and then history and art, since that student is in all 3 of those, right? So we want a complete graph there for that 4th student. CS and bio, so that would be here. Okay, so we have a graph with 5 vertices and 9 edges. Okay, now here according to, so it's to Brooks's theorem, right? We could say that, okay, well, I'm kind of bounded, right, by, excuse me, I'm bounded above here where we look for the smallest subgraph here, right? Or excuse me, from below here, right? So the first thing I want to do is, well, what is the complete graph, the largest complete subgraph here, right? Now I could see that there is a K3 and a K4, right? Now if we think of K3, right, we can think of this graph here. Right, or you have students enrolled in all 3, but that is not the largest subgraph, right? There's actually a bigger subgraph, and that being K4 that I could see here, right? Excuse me. All right, so we have this K4 here where there is a student that here between math, CS, biology, and history. You see there is a connection between all 4 of those, right? So that means that we can't overlap any of those time slots. All right, so it looks like at minimum we're going to be bounded by 4, right? Now one thing we notice here is that there is no connection between math and art, so we can actually overlap that time slot, right? So one formulation here. All right, we could say, all right, I think we can do this. We need minimum 4, and I think we can do it with exactly 4. Because K4 is the largest complete graph here. All right, so if we use slot 1, we can just double up here on math and art here. And then the rest we can just go with slot 2, CS, slot 3, biology, slot 4, history. Okay, and that would be the least number of slots. I couldn't do it with 3, right? Because then I would have a conflict with one of the students. Okay, because of that complete subgraph of K4 in our